Today we're going to talk about working with radicals, so things like square roots and higher roots. And so let's just do some examples. So this radical symbol, square root symbol, means what is the positive or principal square root. And really, you just have to have your times table memorized. So what squared is 49? The answer is 7. We can take square roots of fractions as well. I think the easiest way to do that is you could just take the square root of the numerator and the denominator separately. So what squared is 1? That would be 1. Root 9 is 3. So the answer is 1/3. Now when we were talking about domain earlier, we learned that you can't take the square root of a negative number. So square root of -9, we're going to write that that is not a real number. We'll talk a little bit more about what that means later on. So basically, can't take the square root of a negative number. And that's because when you square a negative number, you always end up getting a positive. Now, if the negative is outside of the radical, this means we're taking the square root of 9, and then we're just making our answer negative. Root 9 is 3, and so the answer is -3. We can take the square root of variables as well. So square root of x squared, that's asking us what squared is x squared? And the answer would be x. If you square x, you get x squared. Although there's actually another possibility. If we take -x and we square it, we'll also get an x squared because a negative times a negative is a positive. And so we can write our answer as absolute value of x. That just indicates that the x could be positive or negative. So same idea in part F. In part F, they're asking us what squared is a to the 4th b squared? And the answer is, well, it could be an a squared b. And how did I get that? I'm using the idea that with exponents, when you have parentheses, you multiply the exponents. So a squared squared becomes a to the 4th. Since squaring something with variables means you're multiplying the exponent by 2, if you want to take the square root of something with variables, you can do the opposite. You can divide those exponents by 2. All right, so using that idea again, our square root of a to the 4th b squared would become a squared b to the 1. But once again, I'm going to put absolute value bars around that answer just to indicate that it could be a negative. It gives you the exact same answer when you square it. All right, we can have higher roots as well, like a cube root. That simply means what cubed is 8, and the answer is 2. And how do I know the answer is 2? Really just by using some trial and error. I know that 2 to the 3rd is 8, so cube root of 8 is 2. Now with cube roots, it's okay to have negatives inside the root, and that's because if you take -2 and you cube it, a negative times a negative times a negative, 3 negatives gives you a negative product. So the cube root of -8 is -2. So to summarize, we can't take an even root of a negative number, so a square root or a 4th root, but we can take an odd root, a cube root, a 5th root, etc. of a negative number. It just gives us a negative answer. We can also take cube roots of things with variables. So if I want to take the cube root of x to the 6, that's asking me what cubed equals x to the 6. And the answer would be x squared. Now, with cube roots, when you take the cube root of something with a variable, you don't need the absolute values. The answer is just x squared. And that's because if I were to take -x squared cubed, I would still get a negative x to the 6. So you only need those absolute values when you have even roots, square roots, 4th roots, etc. The other thing I want to point out is notice that to take the square root of a variable expression, we divided that exponent by 2. And so that means if we want to take the cube root of something with variables, we end up dividing the exponent by 3. If we wanted to take a fourth root, we could divide the exponent by 4, etc. All right, so fourth root of 81, that's asking us what to the fourth power is 81. The answer would be 3, and that's because 3 to the fourth is 81. Fourth root, that's another even root. So we can't take the even root of a negative number. Fourth root of negative 81 is not a real number. And that's because, notice if you take negative 3 to the fourth, you end up getting a positive 81 again. You can never get a negative 81 by multiplying something by itself 4 times. So what are we going to do if we have something that's not a perfect square or a perfect cube? So in the previous example, we always had things that were perfect squares. We were actually able to take the square root just by thinking about the times table. But if we have square root of 75, 75 is not a perfect square. There is no whole number that we could square to give us root 75. And so the next thing we're going to do is talk about how we can simplify that radical. And to simplify that radical, we're going to take advantage of this property right here. If you want to multiply two radicals together, square root of a times square root of b, it turns out you'll get square root of a times b. So for example, what this property is saying in terms of numbers is square root of 2 times square root of 3 should be the same thing as square root of 6. And if you're not convinced, you could double check in a calculator. You could put the left-hand side of that equation in your calculator and then the right-hand side, and you'll get the exact same thing. So we're going to be taking advantage of this property to do the simplification. So let's just start with example 2a. So to simplify this, the first thing we're going to do is see if there are any perfect square factors. So I'm going to see if I can divide 75 by any perfect squares. And I've made a list over to the left of a couple of perfect squares. And so I'm really just checking, can I divide 75 by any of these numbers? And yes, I know that 75 is the same thing as 25 times 3. And 25 is a perfect square. And so I can rewrite this as square root of 25 times square root of 3. That's just using that multiplication principle. Root 25, that's a perfect square. That turns into a 5. And so my final answer is I'm going to write this square root, this radical, as 5 root 3. So the idea is we look for perfect square factors and we pull them out front. We take the square root of the perfect squares. We want to try to find the largest possible perfect square. So for example, if we look at b, root 200, one way you could factor this square root would be 4 times 50. Right? 4 times 50 is 200, and 4 is a perfect square. And so then we could say, well, this is square root of 4 times square root of 50. Root 4 turns into a 2, so 2 root 50. Well, this is not simplified all the way because 50 has another perfect square in it. It has a 25 in it. All right, so then we'd have to say this is 2 times, let's see, 25 times 2. Square root of 25 turns into a 5. So now I've got 2 times 5 times root 2, or 10 times square root of 2. This is the correct answer, and this is a perfect way of doing this problem. However, you'll save yourself some time if you can find the largest possible perfect square before you do the factoring. And so maybe some of you recognize that 200 is the same thing as 100 times 2, and 100 is a perfect square. Square root of 100 is 10, and so notice I get that exact same answer, 10 root 2. So you do want to try to find that largest perfect square possible. If you can't, though, it worked the long way. I was able to factor out individual perfect squares one at a time and just multiply everything together. All right, let's do the same thing with variables. So if I want to simplify square root of x to the 9th, and when you're doing these types of problems in the homework and on worksheets, the directions will say assume all variables are positive. That just means you don't have to worry about putting those absolute value bars in the problem. So we're just going to not worry about negatives. We're going to leave out any absolute value bars in our answers. And most, if not all, of your homework problems will have those directions in them. Okay, so we're going to do the same thing with square root of x to the 9th. So we're trying to factor out, or we're looking for that largest possible perfect square. Now, when it comes to variables, a perfect square is something with an even exponent. That's because when you square an expression, you're multiplying the exponent by 2. So I'm going to try to factor this as something with an even exponent, largest possible one. So I'm going to write this as an x to the 8th times x to the 1. So I broke this down into the largest possible even exponent times x. And then I can do the same thing I did before. I can take the square root of x to the 8th. To do that, I divide the exponent by 2, so I get an x to the 4th. And then I still have an x underneath that radical. All right, let's do one more. Square root of 90b to the 10th. So I'm going to do something similar. I'm going to try to factor out those perfect squares. So I know 90 is the same thing as 9 times 10. And b to the 10th, well, that's already an even exponent. I don't have to factor that one. And then sometimes I actually show a little less work than what I've been doing all along. I sometimes go through and I either highlight or circle the perfect squares. So 9 is a perfect square, and b to the 10th is a perfect square. And the perfect squares come outside of the radical. We actually take their square root. So the 9 turns into a 3, the b to the 10th turns into a b to the 5th, and then the thing that isn't circled, that 10, stays inside the radical. So my final answer would be 3b to the 5th root 10. We can do the exact same thing with cube roots and fourth roots. And so I've made a list of some perfect cubes. You could always use a calculator if you want to find more perfect cubes. And then over on the right, I noticed that if we have variables, and you cube something with a variable, you're multiplying the exponent by 3. So the exponents have multiples of 3 when you're talking about perfect cubes. So same process, just different numbers to think about. So if I have cube root of 24, I notice that 24 is the same thing as 8 times 3. And 8 is my perfect cube. That's going to come outside of the radical. Cube root of 8 turns into a 2, and so I've got 2 cube root of 3. And that's my final answer. So same idea with part F. 250 is the same thing as 125 times 2. And again, I'm looking for factors that are perfect cubes, so I'm looking for factors that come from this list that I generated over to the left. 125 is my perfect cube. Cube root of 125 turns into a 5. So I have a 5 outside of the radical and a 2 left inside the radical. All right, I've got 2 more. So same idea, cube root of 54b to the 3rd. Again, looking at this list of perfect cubes, and you can use some trial and error, just try some numbers on your calculator. I know 54 is 27 times 2. And then b to the 3rd, that's on my list over to the right. That exponent of 3 is divisible by 3. So b to the 3rd is a perfect cube. 27 is a perfect cube. Those are going to come outside of the radical. The 27 turns into a 3. And b to the 3rd turns into a b to the 1. To take the cube root of something with an exponent, I just divide the exponent by 3. And the only thing I have left inside the radical is the 2. So my final answer is 3b cube root of 2. All right, same idea for the last one. So I am looking for perfect cubes, so that would be exponents that are divisible by 3. 10 is not divisible by 3, but 9 is. So I'm going to write a to the 10th as a to the 9th times a to the 1. And then for the b, well, 12 is divisible by 3, so I don't have to do anything with that one. A to the 9th, b to the 12th, those are my perfect cubes. Those come outside of the radical. 9 divided by 3 is 3, so I've got an a to the 3rd. 12 divided by 3 is 4, b to the 4th. And then there's just an a left inside that radical. I can do this process with any type of root. If I have a 4th root, let's see, some 4th powers would be 16 or 81. And I cannot divide 10 by either 16 or 81. And in fact, as soon as I see that I can't divide 10 by 16, it's too big, I know that I can't do anything with the 10. I can't break that down into a perfect 4th power. But for the a to the 10th, something that's a perfect 4th power has an exponent that's divisible by 4. So 10 is not divisible by 4, and I'm just going to go down. 9 is not divisible by 4, but 8 is. So I'm going to write my a to the 10th as an a to the 8th times a squared. And so the only thing I can pull out is this a to the 8th. Everything else will stay inside the radical. So a to the 8th, if I take the 4th root, I divide the exponent by 4. So that turns into an a squared. And then the 10 and the a squared stay inside the radical. We can simplify things that have fractions in them as well. My advice for when you have fractions is to reduce first. I think that'll make the math easier. So what I mean by that is I am ignoring the root symbol, and I'm just thinking about this fraction and noticing if there's any common factors that I can cancel out. Definitely cancel out a 3, because 24 divided by 3 is 8. And I can also cancel an x out of the top. And if I take 1 out of the bottom, there's 3 left over. So I'm actually left with cube root. If I cancel everything out of the top, technically there's a 1 left over, as I divided those terms out. And then I have an 8, x to the 3rd on the bottom. Everything in this problem is a perfect cube. We can cube root the 1, the 8, and the x to the 3rd. So we don't have to do any factoring. We can actually just take the cube root. Cube root of 1 is 1. Cube root of 8 is 2. Cube root of x to the 3rd is x. So this simplifies all the way down to 1 over 2x. So again, if you're asked to simplify radicals that are fractions, try to reduce that fraction first. I think it'll make the math a bit easier for you. All right, I want to show you one more thing before we end today. If you're having a hard time finding the perfect squares or the perfect cubes, if you're really struggling with the factoring, another way you can do this is you can make these factoring trees. So, for example, I know 24 is 2 times 12, and I know that 12 is 2 times 6, and 6 is 2 times 3. So I have basically figured out that 24 is the same thing as 2 times 2 times 2 times 3. I have found all the prime factors of 24. And then the idea is, if you're dealing with a square root, anytime you see a factor occur twice, that's your perfect square. So we've got a 2 squared here. That's my perfect square. That's going to go outside of the radical. So 2 squared, when you square root that, you just get a 2. And then we're left with a 2 times 3, or a 6, inside the radical. Personally, I find it a little bit faster to recognize that 24 is 4 times 6. 4 is the perfect square, so I've got a 2 outside of the radical and a 6 inside. But I think for some of you, the factoring trees might make a little bit more sense. So then if you had a cube root, you could do the same thing. 40 is 4 times 10. 4 is 2 times 2. 10 is 2 times 5. And so this is the cube root of 2 times 2 times 2 times 5. And with cube roots, the idea is if you see a factor occur 3 times, that's your perfect cube. So this is my 2 to the 3rd. That means I'm just going to get a 2 outside and a 5 inside. Again, I tend to just make those lists and I look for those perfect squares or perfect cubes that I have memorized, but feel free to build a factoring tree if you get a little stuck. So that's all I have for this lesson. Please let me know if you have any questions.